Hi, my name's Dan, and this video is one in a series of videos that I'm doing on memory cells using digital electronics, um, and it's part of a larger series that I'm doing in showing the development of a simple 4-bit CPU from basic uh, logic gates. The whole thing's been simulated using this digital works software that I've got up that you can see. So there's a roadmap to where I'm going in this fairly large sequence of videos in the description below. There is also a link to where you can get this software for free, um, and I encourage you to work through the whole thing with me and go from the principle of logic gates, AND gates, NOR gates, etc., to a 4-bit simple CPU. Uh, anyway, the point we're at is we're in the middle of a short series on memory cells. And the previous two videos I did an SR Latch, which is the first bistable, the first basic memory circuit. And then I talked about clocks, and what we want to do is we want to take the SR Latch and turn it into something slightly more sophisticated because it has an enable line, which is typically used by a clock. So you would set up whether you wanted to set or reset, and then you would trigger the actual change using the clock line. So without further ado, let's drag in the SR Latch we created earlier. And just to reiterate again, what we're trying to do, we're trying to adapt this so that we've got an extra input, which is the enable input. So a typical thing that you're going to want if you want enables is to be using AND gates. So you combine um, your somewhat potentially static input, which is the actual information that you want, with and each of them is combined with an AND gate with the enable. So the enable line often goes to several of these AND gates. Like we did last time, or the time before, I'm going to demonstrate it by using inputs and outputs first, and then we'll turn it into a macro, and then we'll test it again, just to check that everything's as it should be. So we've got a couple of inputs, one to each of these AND gates, and then the outputs to the actual inputs that on the SR latch. Connect the outputs together to the LEDs. And we're going to have a third input that I'm going to call the enable. And that's going to go to both of these AND gates. You will see this kind of implementation of enable lines in all sorts of places in digital electronics, right? So let's hopefully demonstrate that this is going to do what we want. So when we turn the circuit on and make it run, it's immediately set itself to Q. And let's remind ourselves, so reset is the one that will change it. If we put the reset line high, nothing's happened yet until we put something in the clock, which is the enable. And that's when it happens. And if we do it again, obviously, because it's on the reset, it's already set, nothing's going to change. We change that back to S, and then we hit the enable. That actually happens. Okay, so it's not a big change, but it is quite important in terms of when we're putting together a larger set of components and we want things to synchronize and happen at various points in time because we've got sequential programming going on. So now I'm going to, as I said we would, I'm going to adapt this and turn it into, I'm just going to make this neater as well at the same time, and turn it into a macro that we can reuse. So that means I'm going to put tags in, tag, 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 and don't need to annotate these because it's fairly obvious where they're connected, the Q and the not Q. I am going to annotate these ones at the top just for clarity. In fact, I'm going to do, I was wanting to make this neater. That's not what I wanted to do. Get rid of that one. Let's try that again. Straight up, across, straight down, and then connect to that line there. Annotation, and we're going to stick in. Let's make it 10 points. That's the S input. Let's our input. We'll take off the overbar, which is there from previously. I want to edit that one to take the overbar off as well. That R needs to move all the way across here. You might be wondering why I'm not dragging and dropping that. I'm just using the arrow keys to move it around. And the reason for that is that I often find with small bits of text, if I, single letters, if I try and grab hold of them and move them, I often end up grabbing hold of the plus, which rotates. So I end up rotating and not moving, and it gets a bit frustrating. So that's the tags that I need. Let's go to the template editor. And I'm actually going to change the layout that we had for the SR Latch. We're going to change the name of this. So when you add an enable to a latch, it gains a new name, which is a flip-flop. You might have heard of flip-flops in digital electronics before. So I'm British, and I find the word flip-flop to be somewhat amusing because plastic footwear for the beach that goes which is just basically a flat bit underneath and a couple of lines that go over your toes. You might know what I'm talking about. In Britain, we call those flip-flops. So the fact that you've got some electronics that's called flip-flops, excuse me, is mildly amusing to British people like me. Australians, I don't know if any Australians are watching, you don't understand this because you don't call those things flip-flops, you call them thongs. And for us Brits, that's even funnier because a thong is a kind of women's underwear in our world. So there we go. That's all kind of by the by. I'm kind of vacillating slightly here because I want to move these around because they're often more useful set up to work kind of horizontally rather than vertically. And so you'll often find when bistables are shown in circuits that they're done with inputs to the left and outputs to the right. I'm just going to move these about. See, I've just demonstrated what I said, which is that when you're trying to move letters about in digital works, you often end up rotating them. Now, is that Q severely rotated? Am I going to be able to rotate it back? I don't really know. Hopefully that's roughly right. S. But where am I going to put the enable? Probably at the top or at the bottom. Bear with me as I move things about on the screen. I don't really know whether it should be top or bottom, but I do know it should be smaller than that. These layouts are in some ways kind of arbitrary. However, sometimes where you are going in a kind of final destination in terms of your circuit can dictate better ways of laying out your templates. Right, so we've created that. We just need to connect up these things into the template. So S needs to connect to the S. So these in the main circuit they're called tags, and in the template they're called pins. and when you use it as a macro, it shows those. It shows the template rather than the underlying circuit. What was that enable? And so these pins are the things that you need to connect the wires to. In fact, as you can see with the SR Latch. And if templates are not something you're used to, then I have a video on how to do it, so go find that. Oh, there's the final one. So we're going to save this macro, save as, and Bistable SR. No longer call it a latch. So if it doesn't have an enable, it's called a latch. A latch if it's a bistable. If it does have an enable, it's called a flip-flop. And collectively, all of these types of things are called bistables. So that's the simple SR flip-flop. Let's create a circuit to demonstrate that this has been done right and that it works. Even though we've just demonstrated it as a native circuit, because it's worth checking that the wiring of the pins, etc., has actually been done properly. So I'm going to once again put in some inputs and some outputs and wire them up. You'll notice in this series of videos that I started right at the beginning of the series by saving my testing circuits, and I've not continued with that habit because I don't really need them saving. It may become the case later on when we get more complex circuits that it's worth saving them in order to make changes. So let's run, and immediately our Q goes high. We're going to do a reset operation, so let's set the reset flag and then give it an enable, and there we go. And we're going to test it again with it at reset, and there should be no change. That is correct. I'm going to change this back to S and enable. There we go. We're still in the situation where we've got both an S and an R, and if I set them both high and then do this, the two outputs become low, and then when we switch that enable off again, in electronics, this would be potentially random as to which one we get. Because this is simulated, it's more determinate, so we seem to be always getting a 0 at the Q when it resettles itself. But this is potentially a small problem that we've got this capability of having both these high. So in the next video, we will deal with that and create yet another version of this bistable. But that's it from me for now.